Hi everybody! Let's continue with design of steel components. A wide flange steel beam carries a uniformly distributed load as shown in the figure, and it's laterally braced at mid-span. Assume CB equals to 1. Ignoring beam's self-weight, what are the support reactions? 2. What is the maximum shear force? 3. What is the maximum bending moment? 4. What is the lightest wide flange section that will carry the load? And 5. What is the maximum deflection? So we have 5 things we have to address today. And we're going to start with calculating reactions. So first things first, I'm going to call this out point A. This is going to be B and C. And I'm going to show my reactions. This is RA. Here I'm going to show RC. So in order to calculate reactions, we're going to do sum of moments in point A equals to 0. And from here we can we have RC multiplied by the arm, which is 20 feet. And RC is in counterclockwise direction. We don't have any other forces in counterclockwise direction, so we're going to go next is minus. We have W, the uniform load, which is 12 kip per foot multiplied by 10. That gives me the resultant force here. So the resultant is going to equal to 12 multiplied by 10. And now we have to also multiply it by the arm, which is 5, equal to 0. So from this equation, we're going to calculate for RC, and RC is going to be equal. And the member at the top, we have 12 multiplied by 10, that's 120, and 5 multiplied, 600. So this gives me RC equals to 30, and these are kips. So we can write down here 30. Next, we can do sum of forces in the y direction, but I always like to take sum of moments in point C equal to 0. So we are going to have RA multiplied by the arm, which is 20 feet. So RA goes in clockwise direction, and we chose it as positive. We don't have any other force in the clockwise direction. Next, the uniform load is going to be minus the resultant, which is 12 multiplied by 10. And now the arm is this arm over here, this distance over here, which is 5 plus 10. The arm is 15 feet. So I have 15 equal to 0. And from this equation, RA equals to 20. Now the top member, we're going to have 120 multiplied by 15. And this gives me 1800. From here, RA equals to 90 kips. So RA 90. And now if we want to verify ourselves, we do sum of forces in the y direction equals to 0. And we're going to take the positive going upward. I'll have 90 plus 30 and minus 12 multiplied by 10, which is 120. And this indeed equals to 0. So we have calculated our reactions correctly. So we are done with point 1 of this problem. Next, we're going to go ahead and calculate the maximum shear, or find out what is the maximum shear. To find the maximum shear, we're going to have to draw the shear diagram. And to draw the shear diagram, I'm going to need my reactions here. So I will do RA was equal to 90 kips. And here I had RC equals to 30 kips. And I'm going to go and draw these lines just like that. And I'm also going to draw this line here where the load changes on the beam. And then the shear, we're going to draw it here. This is going to be the positive. This, we're going to have the negative. And I'm going to just put shear. This is the shear, and our shear is in kips here. We're going to start at 0, and we have this reaction 90 kips. So from this point 0, we're going to go up 90 kips. This is 90. Okay? So now the way we draw a shear diagram, we're going to read the beam and see what happens on this section of the beam. And what happens, we have a uniform load and it's going downwards, and the resultant force of this uniform load is 12 multiplied by 10, so it's 120. So what we know is that from this point 90, we're going to go downwards 120, which means that starting at 90, I'm going to land below the line, and this value here is going to be 30. That's because 120 minus 90 equals to 30. And another thing that I know is that since this is a constant load, a uniform load, my diagram has to look linear. So I'm going to draw a line to connect these 2 points, this point and this point. Wonderful. Now, moving forward, I am at 30 here, and I'm looking at this next section of my beam. I don't have any loading. That means that my diagram is going to look constant. So I'm going to go constant, and then looking at the beam, I have the reaction RC equals to 30. So I have to go up with 30, and I end at 0, which is exactly what I need to be. And it's a way to verify yourself to see if you have drawn your diagram correctly. So we have done a great job there. Negative, negative. Here I have negative, and this is plus. And we can say the maximum shear is obvious here on the diagram, it's 90. So we have done this guy, and now we are done with number 2 as well. Maximum shear is 90 kips. Next, we're going to go we're going to move forward to bending moment diagram. And for the bending moment diagram, we need the areas of the shear moment diagram. And in order to calculate this area, we're going to need, if you see here, we're going to need this distance, right? I'm going to call it out x. And we're going to need this distance over here. So let's see, how do we calculate the distance? And the way we do that is from similar triangles. So I'm going to draw here this big triangle. If I take this line and I translate it upwards over here, I go move this line here with 30 units, that means that this point is going to move up with 30 units. So now this line is going to be situated somewhere here, which means that this total distance is going to be 120. And then here I'm going to land at 0. So what I will have there is 120 for this value here. This distance, we know it. This is 10 units. So this is going to be 10. And now I have this similar triangle. which this value we know it's 90, right? And the value we don't know is x. So from these two similar triangles, we're going to calculate for x. All right? So the way we do this, we're going to work with this side 120 over 90 is equal to 10 over x. And from this equation, x is going to equal to 90 multiplied by 10 divided by 120. The way this works, we multiply these two, and then we divide by this opposite member to x. And this is going to be equal to 7.5 feet. So now we found x. That means we can also calculate this value over here. If x is 7.5 and the total distance is 10, that means that this small distance here is 2.5. And why we calculated this, we need this for our, or to draw the bending moment diagram. So now I have the clean page. I'm gonna go down. I'm going to prepare to draw the bending moment diagram. I'm gonna draw this line in the middle. Let's see, moment diagram. This is in Kip foot. There you go. And now, you know, if you've watched my videos, you've noticed how I sort of switch the sign of the diagram. I do negative at the top and positive at the bottom. And I do explain why am I doing this. But in this case, just because I want to keep it consistent with the FE exam, I'm going to keep the plus at the top, and I'm going to also show it here, negative at the bottom. I'm going to go back to our shear diagram because we also have to calculate the areas. So the area for this first triangle, I'm going to say area equals 2, and it's going to be 90 multiplied by 7.5 over 2. Right? And now this area over here, we are going to have 30, say A2 equals to 30 multiplied by 2.5 divided by 2. This is just the area of a triangle. It's the base multiplied by the height divided by 2. And now this area number 3, which is the area of a rectangle, we have 30 multiplied by 10 equals 300. Here, A2, let's see how much is that. Got 30 multiplied by 2.5, 2 divided, that gives me 37.5. So this A2 is 37.5. And then A1 is 90. 7.5 multiplied, 2 divided. It's equal to 337.5. So A1 is 337.5. Wonderful. So now these values, we are going to use them for the moment diagram. So let's go back to the moment diagram. What I am also going to do, since our shear diagram intersects somewhere here, this distance is 7.5 and this is 2.5. I'm going to draw this line, continue this line all the way downwards. Why is that line important? Is because where the shear diagram intersects, or where the shear is 0, there's a maximum or a minimum. So we need this line to show our maximum or minimum in the moment diagram. So what I'm going to do here as well, I'm going to bring the area. So area for this first section is 337.5. For the second section is 37.5. And for this section of the beam, we have, I believe, 300. There you go. Wonderful. And, it's kind of tricky here because usually when you draw a moment diagram, you need your shear diagram. Kind of draw your moment diagram based out of your shear diagram. So I always like to have them together. It happens here that I just kind of started this way, so I'm going to continue, but we're going to go back and forth and look at our shear diagram anyway. Great. So I'm going to start here. Let me take another color. We are at the support. The moment at this support is 0. We're going to start at 0. Now, looking at the shear diagram, we have a triangle that goes from a big value to 0 here. And it is positive, so we're going to go in our moment diagram towards the positive side, which means we're going to go upward. And another thing is this shear diagram is linear, which means our moment diagram is going to be parabolic. Okay? So let me draw this triangle, therefore, to talk about something. So our triangle in the shear diagram looks like this. All right, positive, and it looks like this. And in my previous videos, again, I'm going to bring that up, is that I'm talking about how are we going to draw the diagram? Is it going to look, let me draw this line. So we start at 0, and how am I going to draw it? Like this, sagging, or, this way? And to answer this question, if you've watched my videos, I'm making that analogy with a ski slope. And what I mean, I'm going to explain that again. So look at this value, or look at this triangle. We're going from a big value, and the value gets smaller and smaller and smaller, 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 all the way until it gets 0. If you make the analogy of a ski slope, imagine you're going to go fast, right? And then you're going to slow down. So fast and then slow, which means I may delete this now. If I start from 0, and the value that I need to have here, in my case, 337, right? I'm going to have 337. So I have to go fast and then slow. That means I'm going to go fast and then I'm going to slow down. So let's try that again in our case. We have 337.5 towards the positive side. So I'm going to add this value here. This is 337.5. And we're on the positive side. And our shear diagram looks like that. So we're going to go fast and then slow. So let's try. We're going to go fast and then we're going to slow down. Okay? And this is positive. Great. Now, next piece of the shear diagram looks like this. Okay? And it is, if we do the ski slope analogy here as well, first we're going to talk about the fact that this shear diagram, it's negative, which means we're going to go downwards towards the negative side. That's one thing. Another thing, that this shear diagram is linear, which means our moment diagram is going to look parabolic. And then let's also now talk about that ski analogy. So our triangle in this case goes from 0 all the way to this value here, to big value 30. So now, if we think of a ski slope, we're going to go slow and then fast. So small, big, slow, fast. So from this point, we're going to go downwards with a value of 37.5. So 37.5, which means we're going to land somewhere here. And 337.5 minus 37.5, this value is going to be 300. And I'm making 3,000. I meant 300. Wonderful. So let's see now. How do we go slow and then fast, right? Can you see this now? Maybe better. Slow and then fast. Because if this was sagging, like if my triangle was looking, let's say the other way, if my triangle was looking this way, I make the analogy of fast and slow, the ski analogy. I would have gone fast and then slow, right? I kind of exaggerated there a little bit, but it would have looked like this. Fast and then I slowed down. So this diagram was sagging. If my shear diagram would have been like this, but it's not. So we have it right here. We draw it the right way. Wonderful. And now we are at 300. And my shear diagram, if you remember, it looks constant, right? And it's negative. We can also go back and check. There you go. And the value of this is 300. So what that tells me is that the moment diagram is going to look linear. So from this point, 300, I'm going to go with a value of 300 towards the negative side because the shear diagram is negative. So I have to keep going towards the negative side. And if I do that, I'm going to end up right at 0. And this is positive, and this is linear. And I end up at 0, which is great because at the support, the moment is 0. This is what we need to have. And there you go. This is how we just finished drawing the bending moment diagram. And the maximum bending moment, it's here at this point, and it's 337.5. And it's where shear diagram intersects this line where, shear is 0, the moment is maximum. Wonderful. Now let's go to number 4. Number 4 says, what is the lightest wide flange section that will carry the load? Now, how do we solve this one? Okay, so here we're going to go to FE Handbook. And I wanted to show you in the civil engineering under the structural engineering, right? The civil engineering. We're going to go all the way down to steel design, structural design, and keep going downwards. Short columns, concrete, there you go. Design of steel components. Over here, there's a table somewhere here at the end with, there you go, this table. Available moment and braced length. So on this side, we have the available moment. On this side, we have the embraced length. And based on these two values, we can find a beam that is capable of supporting this moment. But the beam has to have a certain unbraced length. So in our case, we have the unbraced length of 10 feet because our beam is laterally supported in the middle, which means my unbraced length is 10 feet. So I'm going to place myself here and move upwards. And then I'm going to come back here and say, well, what is the moment? So if you, in the FE handbook, you're given that phi mn nominal moment equals to mu. Now, in my case, mu, the maximum moment, equals 2. And this is an interesting that I wanted to bring up is that the moment, you can calculate it as we've done previously. You can calculate it as we've done in this case, right? Our moment is 337.5 kip foot. But if you are given this simply supported beam and you are asked to calculate the maximum moment, you don't have to go through all of this work and calculate the reactions and calculate shear diagram and then the moment diagram because it's going to take you a lot of time and you don't want to lose time on the exam. You want to figure out a way to do this faster. And the fast way is to know that under the mechanics of material, that the last page of mechanics of materials provides you with moments, maximum moments for a certain loaded beam, simply supported beams that are loaded with a point load in the midspan, point load at a certain distance away from midspan, so on, so on. And in this page, on this page, we have the case, our case, where we have a simply supported beam and we have a uniform load halfway. And here you are given the maximum moment. And it tells you that it's at 3/8 of the length, and it gives you this value over here. So I'm gonna, even though we have calculated the moment, I'm gonna go ahead and calculate it based on this formula. So 9/128, let's go down. So let's say you have to calculate maximum moment. You haven't done all of the work we did so far. So we're gonna go to mechanics of materials, get our formula, and I'm gonna say that, so here mu equals to 1.2 m max, right? Mu is the ultimate moment, and it's factored. So now m max, I'm gonna say, what was it? Was 9/128 multiplied by the load, WU, multiplied by the length power 2, L power 2. And we're just going to substitute 128 multiplied by 12 and multiplied by L, which is 20 feet power 2. And let's see what is this going to give me. So we have 20 squared, 12 multiplied, 9 multiplied, 128 divided. And guess what? I'm getting 337.5, which was expected, right? Because this is the value we have calculated before based on calculating reactions and shear diagram. But see how fast was it to just look up the formula and substitute. So it's very important to know where your formulas are, but you're gonna get there. Anyway, so now we can calculate mu. So mu is 1.2 multiplied by a max, which is 337.5. And if you multiply, you're gonna get mu equals to 405 cube foot. And why am I calculating mu? Because from this is actually greater. So phi mn has to be greater or equal with mu. And from here, we're just going to say phi mn equals to mu. Because if you go back to the table that I showed you, and that table is under the civil engineering. Let's go downwards. We're going to scroll up a little bit. Available moment via some braced length. So we're going to go upwards. The table is somewhere here. There you go. We're getting closer. There you go. Available moment on braced length. And this table, you have to be careful that it has to have CB equals to 1, which in our problem we are told assumes CB equals to 1, Fy equals to 50 KSI, which in the problem we are given Fy give 50 KSI. So the value for phi mn, design moment, we have it at 405. And we also know that on braced length it's 10. So what we are going to do, let me move this page in such a way that it's I'm able to see while I moved it too much. Hold on. There you go. So if I take this span and I'm gonna go from 10, gonna go, the straight line. Well, that's not very straight, but all the way up until I intersect with 405. So I'm at this point. So now what I need a beam that is from this point upwards, because I need a beam that can support this load and more, at least 405. So the next straight line here is this one over here. So we have W21 by 55. So the beam that is able to carry this load, the wide flange beam, is W21 by 55. So based on the table in the FE handbook, page 286, so table 310, let me write down table 310. So from table 310, from the fact that our unbraced length, LB, equals to 10 feet, and phi MN equals to 405, it results that the W section that can carry the load is, let me go back because I forgot, is W21 by 55. 21 by 55. And this is how you use the table. Next question, what is the maximum deflection? So we're going to go to a brand new page, and for maximum deflection, I'm going to go back to mechanics of materials, to that table there at the end of mechanics of materials. This is the beam that I have loaded with a uniform load only halfway. And over here, you're given the deflection. And let's pay attention here. We're given the deflection at half span, right? It's this value here. But we are not asked at mid span. We're asked what is the maximum deflection. And in this case, the maximum deflection is at this distance from the left, right? And from the left support, I mean, and the maximum deflection is minus because it goes downwards, 0.006563 WL power 4 multiplied by module of elasticity and moment of inertia. So let's write this formula down. I'm going to say that deflection equals to minus 0.006563 WL power 4 divided by modulus of elasticity and multiplied by moment of inertia of the beam that we know now what it is W21 by 55. So now some things that we can do here, or we should do, is modulus of elasticity for steel. If you don't know it, it's also given in the FE handbook, and it is also under mechanics of materials. There's a table here somewhere. So modulus of elasticity for steel is 29 mega pounds per square inch, which gives you 29,000 KSI. Mega is 29 times 10 power 6. Giga is power 9. So we're going to do KSI is power 3. So we're going to have 29,000 KSI. Okay. So for steel, we have 29,000 KSI. And KSI is, if you're not familiar, kip per square inch. I'm just going to put it out there just in case. And then moment of inertia for this beam, we're going to go to not under mechanics of materials, that is under the civil engineering. We have to scroll the way down to design of steel components. I can say that. Design of steel, and gets you to this page. If you want to speed up the process a little bit, and we're going to scroll down to, look at that, 2155, 2155, and right here. And we have, well, this is not a table because we need a moment of inertia. Oh, actually it is. There you go. Here it is. So we have moment of inertia is 1140 inch power 4. So I'm going to write down 1140 inch power 4. And wonderful. So now what we should do is just come here and substitute. So I'm going to write minus 0.006563 multiplied. And another thing to remember is that we have inches, and then at the top, the uniform load is given kip per foot, and the length is per foot. So you have to pay attention. The length is in feet, so you have to pay attention to units. So let me write things down for now like this. I'm going to say 12 kip per linear foot. Okay. And I'm going to multiply right away. 1 foot equals to 12 inches. And that's going to get rid of feet, and I'm going to have inches. Okay. Wonderful. Next, this is multiplied by, and I have L power 4, which is 20 power 4, to have feet power 4, right? And in order to get rid of feet, we're going to have to do well. We have 1 foot equals to 12 inches. Foot power 4 equals to 12 inches power 4. And there you go. Now we can get rid of this. And we're going to be left with inches here. Now at the bottom, we leave the units the way they are. We have kips per square inch and multiplied by moment of inertia, which is 1140 inches power 4. Great. So all we have to do now is just do the math and pay attention to calculations. Okay, so here I'm going to have 12 over 12. These two go away. Okay, now here 20 power 4. Let me do that. 20 power 4. Okay, and then we have 12 power 4 multiplied. And then also we multiply by this value over here, 0.006563 multiplied. Great. Now at the bottom, 29,000, 1140 multiplied, and then divide. There you go. And I get that the deflection equals to get minus because it goes downwards somehow like that, right? And I get maximum deflection. Here it's downwards, that's why it's negative. 0.6586. So I'm going to do 0.66 inches. There you go. And we have also calculated deflection. I hope you were calculating with me. If you find a different value, please feel free to leave a comment in the section below, because I have checked my calculations only once, so it's possible that I've made a mistake, and let me know in the comments. I hope you found this helpful. Problems like that are on the FE exam, and the more problems you do, the better prepared you're going to be. As always, if you found it helpful, don't forget to subscribe and give it a like, because this helps put this video in front of more people just like you. Keep up the good work on practicing the FE problems, and I will see you next week.